Well, hello everyone. I am back Kimani, the AI/ML track lead at Google Developer Groups, Chuka University. And today we shall be going through unsupervised learning. For the previous sessions, we've been looking at supervised learning, and for now, we are going to delve into unsupervised learning. So, unlike supervised learning, there are no target labels. So, we're just stepping into one of the most fascinating realms of artificial intelligence, that is unsupervised learning. And while most people are familiar with AI that predicts specific answers, like the stock price of or a cat versus dog image generation or identification, today we'll focus on how machines find meaning in chaos of raw and labeled data. So, some of you might be asking yourselves, what is unsupervised learning, right? So, unsupervised learning is in unsupervised learning, we are teachers giving a computer an answer key. So, in unsupervised learning, the computer is an explorer. So, there are no labels. So, we provide the output and so we provide the input, so which is our input data, which is X, and we ask the machine what is the structure here. So and it's the difference between following the map and also drawing one from scratch. So yeah, so primarily we shall look at clustering. So unsupervised learning is grouped into three. We have clustering, association, and also dimensionality reduction. So um, let's just go to this slide. So clustering is so imagine you have a bucket of 1,000 of mixed Lego bricks, right? And you don't want the computer to find um, the red squares. So you just say group this by similarity, and the goal is high intra-cluster similarity. Things in a group should look alike, and high intercluster separation is groups should be as distinct as possible. So intra-cluster similarity is points in the same groups should be similar, and inter-cluster similarity is where points of different groups should be different. So, and this can be applied in various sections. So we can apply it in customer segmentation or in image compression or also in anomaly detection. So we shall go to part one, which is k-means. So we are actually going to look at two parts, which is k-means and hierarchical clustering. So in k-means, uh, first our algorithm is like the bread and butter of machine learning. So in k-means, uh, and this is what is called k-means. So k-means is the centroid based algorithm, and it is mathematically we are trying to minimize the within cluster. So we're trying to minimize the within cluster sum of squares, so which is the WCSS, and essentially we just want to we want the distance between every data point and its assigned center to be as small as possible. So if you'd love to know how k-means works, it chooses a number of clusters, which is k. So so the beauty of k-means is its simplicity. So there are 4 steps. It's like a 4-step dance. So one, it chooses a number, and this is a number of clusters which can be we can denote it as k, and then it drops the k random points, which are the centroids, into the data, and then every data point attaches itself into the closest centroid, and then the centroids move to the mean of their assigned points, and then yeah, so and then we just repeat step 3 and step 4 until the centroids no longer change. So yeah, it's like an iterative search for balance. So give me 1 second. Just a second. So yeah, that is how k-means works. And so can you just give me 1 minute? Yeah, so I think we shall just have to move to slide and here we are trying to choose the optimal k. But how do we know if k should be 3 or 5 or 10? So we use the elbow method. So and the elbow method is where we add more clusters. And and the error, which is the WCSS, goes down, but there's a point of diminishing returns. So we look for the elbow in the graph. That is the point where adding more clusters doesn't significantly improve the fix. So yeah, so this represents the balance between maximum groupings and also minimum complexity. So that is how we choose the optimal k. And we shall try do a hands-on. We'll do that afterwards. I just want us to familiarize ourselves with the theory part of it before we delve into the practical part of it. So yeah, so um, so we shall. I'll talk about hierarchical clustering so that we can go into the hands-on. So unlike the k-means, it does not require a preferred k. It just creates a tree hierarchy of clusters, and there are uh, for example, if k-means is k-means is like dividing pizza into slices, and hierarchical clustering is like building a family tree. So we don't need to pick k up front. We just look uh, at how closely related every point is to its neighbors. So yeah, um, so we also do have two types of uh, hierarchical clustering, and that is the Agglomerative, that is the bottom up. So we start with each point as a cluster and then we merge them. And then we have the divisive, that is the top down. So we start with one cluster and then we just split it. Yeah, so uh, there's also something we call linkage criteria. And the question you're supposed to ask yourself is, how do we measure distance between clusters? So the secret sauce here is linkage clustering. And how do we define distance between two groups, like I asked? Do we look at the closest members that are single, that is the single linkage, or the farthest, that is the complete linkage? So, or maybe the average, or so in our code today we shall use the words method, to which minimizes the variance within clusters, and it also tries to keep our clusters tight and compact by minimizing variance. So yeah, And then we shall also do a dendrogram, and it is just a visual representation of hierarchical relationship. So where the y-axis represents the distance or the dissimilarity by cutting the dendrogram. So by cutting the dendrogram at certain heights, we determine the number of clusters. So think of it as a DNA map of your data. So the higher the vertical line, the more different the groups are. And by drawing a horizontal line across the tree, we're just trying to decide how many clusters we want to keep. So yeah, we shall do a hands-on on this as well. So keep up with me. So yeah. So I think we shall just jump into the hands-on part of this so that we can like fixate on what we have just said. So if you're using Google Colab or you're using Twitter notebooks, feel free to use whichever you're comfortable with. So yeah, let's uh, let's do. So I'll just create new channel. So just give me 1 second. So just like supervised learning, we shall still use sklearn. So don't you worry. So we shall import the essential libraries. So and then we shall try to do we shall also try to generate some synthetic data. So we shall try to generate synthetic data. Then later we shall just visualize our raw data. Sorry. Yeah, and then we shall just apply k-means. Just a second. I should apply k-means. Should apply k. And then we shall just do a plotting of the clusters. A plotting of the clusters. Yeah. So, and then now we shall move into the hierarchical. We shall move into the hierarchical clustering. So let's start. We shall import matplotlib as .pyplot, sorry, as plt, and then from sklearn dot cluster we shall import k-means. And then also from sklearn.dataset we shall we are going to import matplots. I'm sure we have interacted with matplots before, so it shouldn't be difficult for us. So yeah, and then we shall try to generate some synthetic data. So surely just change that datasets. We shall try to import some synthetic data. So yeah, should say make blobs. Then we say n samples. And then we just equate it to 300. And then we put centers equal to 4. And then we just cluster standard. And then just equate that to 0.60. So and then random stage is just equal to 0. Yeah, so we run that. So we shall try to visualize our raw data. So we just do a plt. So this is where matplotlib comes in. Dot scatter. So we're trying to create like a scatter plot. So yeah, and then sorry, 0, and then x, then and then I just say plt.show. plt.show. So if we run this, yeah. So there we do have our scatter plot. So we're just going to just try and apply our k-means. So this is where we like try to do an implementation of our k-means. So just say k-means. Um, and we just equate that to k-means. And we just say and clusters. Just equal that to 4. And then we initialize. So init. Just say k. Oops, sorry. K-means plus plus. Then I just max, and then we just iterate. And this it is to 300, and then we just and initialize and init, then we just equate this to 10. Yeah, so that is it. Let's just run that to see if we have any errors. Actually we do. So great. So what we'll do is just do a y-means. So and our y-means just our k-means. So our variable k-means k-means dot fit predict, then we just put that to an x. Yeah, so if we run this, yeah, so we shall try plotting the clusters. So we shall do a plt dot scatter. Sorry, plt dot scatter, and then we just Just give me 1 second. Just a second. Just give me a second. This goes to variance. Yeah. So we just do centers, and our centers will be k-means dot cluster, sorry, k-means dot cluster. Do centers. Yeah, so and then we just do scatter. We just do some plt.scatter, and we just copy this line. Then we just go changing. So centers, and so this one we'll change it to color. Just say C is equals to red, and then just say S is equals to 200, and then we just equate an alpha. Sorry. Then we just equate an alpha to 0.5. Then just do a plt dot title, and then we just give our plot a title, so we can decide to give it a k-means results. Yeah, and then just of lt.show t.show. So let's run this and debug where necessary. So so the second, okay, did some supposed to be off. So let's run this. Yeah, so here we do have our plots scattered in different clusters. So that's how it's supposed to be. So yeah, so basically we just uh, give me a second. Yeah, so you can actually see that our k-means results have been separated in different colors. So for easy clustering. So uh, with that, I think we can move to the hands-on hierarchical code. So this is where we'll be trying to draw the dendrogram. Okay, so I think we shall import libraries. So and then we shall create dendrograms. So sorry, we shall create dendrograms, and then later we shall be fixing hierarchical clusters. So fit in. And then we shall just do some visualization. Sorry, we shall just do some visualization. So great. Let's start by importing the libraries for the hierarchical clusters. So we're going to import skipy.cluster.hierarchy. Yeah, as and then we'll just create dendrograms. So we shall still use matplotlib to do this. So dot figure. So we shall do some fig size. And then which will be equal to 10. And 7. So it will all make sense. So sorry. And then just do a dendrogram, which is sch dot dendrogram, which is sch dot linkage. Is equals to what? And then we shall do a plt.title. We just name it dendrogram. Dendrogram. And then plt dot we shall label the x-axis and the y-axis. So label so just name it samples. Sorry. And then shall do a plt dot y size, y label, and then we just label it to then do a plt.show. So here it is. So you can actually see that we have actually visualized it. I wish I could have tilted it a little bit. So yeah, you can actually see the comparison between the Euclidean distances and the samples. So we have actually been able to draw a dendrogram. So interesting as it is, that is how a dendrogram actually looks like. So you can see it's branching. It's more related to decision trees. It's just that um, there is a variation in that. Uh, so we shall try to do a fitting of uh, hierarchical clusters. So from sklearn, from sklearn.cluster, we're going to import, sorry, import, we're going to import, it's a very long word, agglomerative clustering. Yeah, so here we should just do HC. So HC is equals to, I'll just copy this word so long. Control V. Just say end cluster be equal to 4 and affinity will be equal to Euclidean. And then our linkage will be equal to what? So actually we shall do so we shall do a hc.c.fit, sorry, hc.fit predict x. Let's see if we run into any bugs. So end cluster. So we're good. So we shall do a visualization. So just copy, just plt dot scatter. But I put an O there. Then X, just So we just change a few things. So um, maybe one. So maybe one. Then we should change our color to blue. Yeah. So then we just give it a plt dot title. Yeah. And then plt dot show. So yeah, you can see that we have been able to do hierarchical clustering where uh, our our uh, give me one second, where it is a visual representation of the hierarchical relationship, and where our y-axis represents the distance, and by cutting the dendrogram at certain height, so our height has been say 5.5, we determine the number of clusters we have. So yeah, that is it. So give me one second, and then we shall conclude. So I don't think there's much to do afterwards, but you've been able to see how clustering and k-means differ. So if we try to do like a comparison table, in terms of sorry, in terms of features, and also in terms of um, so let me just look for a place I can. So in terms of feature, so that is the difference between k-means and the hierarchical. In terms of efficiency, k-means is very scalable, and the hierarchical structure is kind of slower on larger data sets. And on cluster shape, you're able to see that the k-means um, is more spherical, and our k-means is more spherical, and our hierarchical is based on any shape. So it can, and this is mostly dependent on linkage and parameters. K-means requires k, and our hierarchical just requires linkage types. And in terms of stability, k-means is very can vary. So it is in terms of initialization, but hierarchical is more on its decentric. So yeah, unsupervised learning is fine structure in unlabeled data, and k-means is faster, and it's great for spherical clusters, and hierarchical provides just a richer visual tree. That is, for example, the dendrogram, um, or dendrogram. Yeah. So try it yourself. Use the iris or the uh, mall customers or whichever data set you have, and try to do it. Try to form C1 scikit-learn and practice more. So yeah.